important is. So, good afternoon. Thank you very much for your participation, and more thanks to our guest lecturer on this week's Athena talk that is organized by the Hellenic Mediterranean University and the International Office. It's a great pleasure to welcome Professor Yen Hung Lin. All of us in Greece and in Crete, we know Professor Lin as Yen. He has a very nice and impressive, I would say, career path. Yen, he was a PhD student of Professor Anthopoulos, and then he moved to Oxford, if I'm not doing a mistake. His research work has received more than 4,500 citations. His age index is 39. His research activities include device physics, perovskite, photovoltaic, thin film electronics, and I think that today's talk is very much focused on photovoltaics, particularly the perovskites, which is like one of the candidates, one of the competitors of, they would like to say, of the silicon solar cells. And now Professor Lin Yen, he's a professor in the University of in the Electronic and Computer Engineering Department of Hong Kong University of Science and Technology in Hong Kong. And as we can see, Hong Kong is a very beautiful area, you know, from the picture that Yen has just shared with us. We are going to upload, I would like to say to you before I give the floor to Yen, that Yen also has visited our university when he was not younger, because he looks young still, when he was a PhD student in Imperial, in this summer school that we were organizing in organic electronics. And we are very happy with his progress and his career. So Yen, the floor is yours for the next, let's say, 40 minutes, and then we are going to discuss. Thank you very much for your participation.
All right, and Kostas, and hello everyone, and very nice, very kind introductions and describe my whole careers. And of course, I've been to Crete, and a beautiful place, probably the best summer school, winter school that I had a chance to go to. And now I moved to Hong Kong, like in just 1.5 years ago. And everything's new to me and very different from Europe, from the UK. I continue my journey in perovskite solar cells. And today, my talk will basically divide it into two parts. The first part will be describing a work we published a couple of years back. But we use this kind of thing as motivation that we try to do more in terms of how we polish perovskite, actually just like many other research groups, like to passivate defects, and we look into perovskite from different angles. So perovskite is a very interesting material, especially compared to the most widely applied material, that is silicon. But unlike silicon perhaps has one defect in this kind of a large area, 1 square centimeter. But for perovskite, it's not so much. And actually, we can practice from solution, as many of you know, and also people are working on organics, know about the different transport mechanism in this kind of new material, novel material. But I just gonna dive into why it's attractive, because it brings this kind of commercial opportunities, like making tendons. Just to give an example, if we try to build a 1 megawatt PV panels, we just use a tiny bit of material as compared to silicon. Most of them are also about the material, and of course there will be still a lot of things we have to consider about the manufacturing facilities and also how we handle solvent if we really go down the solution process and do. But just from very, very simple angle, like we think about materials, maybe a bit naive to say, but still it's impressive how little amount of material we need in order to build and to manufacture so many panels. All right, so this is just an example using a root that perovskite just crystallize straight away when we do solution process. If you think about, if you today you do bar coating, slab die, and different large area solution processing method, when you coat it, you will just crystallize right away. And perovskite is of this kind of ABX3 structures like A side monovalent cation and divalent cation for the B side, and X side normally is halide. And we know there are a couple of candidates that we can use, not just mesammonium, also from medium, these kind of things. As long as you follow this Goldschmidt tolerance factor, then we'll be able to form a perovskite. But of course, different size of the atoms of the molecule we use, we not necessarily to form cubic structures will have a strong bigger strand or these kind of things. That might not be ideal. But the one thing very important is when we talk about perovskite, just like, oh, this kind of material is not stable. Are we able to make it stable? Maybe. So this is just an example. We use a mesammonium-based perovskite materials as compared to this kind of a mixed cation, cesium for medium I just talked about. And we simply age the perovskite film in nitrogen at 130 degrees Celsius. You can see it is color for mesammonium-based perovskite because it simply decomposes. It locks the structures and locks the perovskite structures. But cesium Fa, at the time, people still exploring this kind of compound like almost 10 years ago, like 8 years ago. So this is a work done by my colleague to try to use this kind of mixed cation perovskite to make a more stable compound. But perovskite actually contains many kind of defects. So no matter what kind of different atoms molecule we use, it forms defect naturally. And the simple things the community do is try to additive and try to fix those defects, imperfect sites with additional or foreigner atoms or molecules. So in this work, the first thing the first part I'm gonna talk about is the work we published a couple of years back. So this kind of additive is the one we chose to use. Is ionic additive. It's similar to ionic liquids. Why is that? Actually, we found quite interesting properties. But as you can see here, it contains a cation and anions. And anion is slightly, actually, with a comparable size as X side in a perovskite. But I think so far no one actually found this kind of pseudo halide actually forms part of the perovskite structures. But this kind of large cations actually it cannot go into perovskite structures. What we do is that actually it will be pushed out of the crystal structures. And we did how is that this kind of additive? So back then we did some simple experiment, just try to use different ionic additive. So the same cations, but different anions. Like the anion is here is BF4, but the anion of iodide, bromide, and chloride. But something interesting is that we found we mix with one of the perovskite precursor, which is iodide. It forms complex. Which kind of compound form complex is the one contains halides. So actually, when we add additive, sometimes it forms this kind of complex. So it's a structure we don't want. Actually, destroy the later on if we try to add all different precursors to form the perovskite structures. So BF4 somehow actually it doesn't actually form this kind of strong coordinations a complex, so it becomes a good candidate. So we simply blend this kind of additive into perovskite precursor. We deposit films and we form this kind of polycrystalline film. And we try to identify exactly where the whereabouts of this kind of ionic additive. So we use 12 things. So the animation you see here is actually we taken out layer by layer. It's higher resolution and things. Um, so we will be able to actually to construct the distribution of these organic molecules. You see it's a little bit lumpy here because you see a cluster-like structures here. But when you look at the scale here, it's only 10 micrometers. This is in terms of the scale we are talking about for laboratory-made photovoltaic cell is quite uniform. But of course, this kind of lumpy property actually indicates what we believe the additive is pushed out of to the grain boundary. This kind of apparent grain boundary that we can observe by an SEM scanning electron microscope. Because as simple as that, most of the time we add additive, it will be pushed out if the structure is too big because it doesn't incorporate into the perovskite structures. So this kind of behavior is mostly actually approached by the community because what we believe the very vulnerable part of perovskite is at the grain boundary, this kind of apparent grain. So this kind of additive being pushed out, it thinks that what we believe is it will stop the material coming out. And we're going to look at that in a minute. But for most of the work you see from the community, we do as part of the community, we do some optical spectroscopic characterization. For example, we also did the same things like optical palm terahertz probe tracings here. But compare these two, actually, one is the modified film, the other one is control film. There's not much difference. So what it indicates, I just gonna jump to the conclusions. So basically, the modification doesn't modify the electronic structures. The electronic structures remains the same. So this kind of a property is the same. But something even more common is like we do TCSPC, like time correlated single photon counting, this kind of transit, like or TRPL, to understand its lifetime, to do a little bit of um, um, estimation about this kind of exponential decay that I show in these equations. So we have the K1, we have the K2. K1 is the constant for for the monomolecular recombinations. K2 is for bimolecular recombinations. But the something odd here is when we compare this kind of a modified one and the control one, the K2, there's a difference, a significant difference here. But when we look at the another transient method using terahertz, the electronic property doesn't change after modifications. Actually, you can think about this kind of additive being pushed out of the crystal structures. So assuming we don't actually to modify the majority of the perovskite itself in the bulk. So what happens here? We have different bimolecular recombination rate. So this is actually if we consider the fact the terahertz will be the accurate measurement when we do this kind of factings, that might include some wrong estimations. So what happens if today we assume the K2 is the same, which means we have exactly the same electronic structure. I shouldn't say exactly the same, I mean similar, the bulk properties. Then we fit the transient here. So what we found is actually at the interface, we have very different carrier dynamics. What it means is actually we have not the same amount of charge carrier of opposite polarity. Basically, electron and hole concentration is not the same. So this kind of things actually is quite common to see in a perovskite because perhaps you heard about the stoichiometry cause this kind of a perovskite of few hundred nanometer. The composition may not be the same. This is one thing maybe to cause this kind of uneven and charge carrier distribution between opposite polarities. So if we don't have a balanced charge carrier, then the monomolecular recombination will of course increase. So this kind of thing actually to verify, we reduce the frequency. You can see this kind of when we reduce the frequency, the behavior of trap state will be amplified. So you won't be able to actually to populate so many charge carrier to the excited state. So when we have a lower frequency, we don't see much change when we have an ionic additive, which is really modify a perovskite. But what we see here, we actually see a massive difference in control, especially when we change the frequency. Basically, we can amplify the effect of the trap state. All right. So this is what we think what happens from this kind of film characterization using this kind of electronic measurement method. And one thing important in perovskite as compared to silicon is to carry out the stability test. So the stability test, the one more difficult one is the one to combine light and heat. What we found actually from our result is that we have very different. We have improved the stability a lot by using this kind of additive. As compared to the reference one, it has more than it roughly has 3 to 4 times enhancement. And the upper one is unencapsulated cells, and we do it and under this kind of full spectrum sunlight contains the wavelengths, including basically matching the solar spectrums at 6 degrees Celsius in air. And as compared to reference, the data showing here is the one we encapsulate the cell, but using exactly the same aging machines under the full spectrum sunlight at 85 degrees in air. All right. So the important things what we found in this work is actually to identify the degradation product. We now know about the functionality of this kind of additive, what kind of it does to the bulk perovskite. And next thing is actually about to identify degradation product, because in this way we'll be able to reverse engineer and to reverse engineer the perovskite material basically to extend its lifetime. So what we did actually, we prepare 2 different perovskite film, and one is control, one is with modified film, and we age this film in exactly the same condition as how we age our cell, the one you just saw. And what you can see here is that we have something very different happens at the smaller angle when we carry out this kind of X-ray diffraction patterns. So what we found, the degradation product is actually different phase formations. Although it's very small, but it exists in the field, especially when we look at the angle between 10 to 20 degrees. And what we found is actually the formation of FAPBBr3. I forgot to mention one thing. The perovskite we use is mixed cation and mixed anions. The anion, the bromide content is around 25%. And what we see here is actually we have different perovskite different precursor material coming out of the main phase. So what does that mean? So we have different iodide and different different oxide. So we have different anions. So we have iodide and bromide. And of course, this is iodide-rich perovskite material. And when we have this kind of material, it's easier to control its band gap for tender applications. But there's one thing, the halide might segregate. So what we see here is the phase formation, secondary phase formation. And from UV-Vis data, what you see here, when we see this kind of control film, initially at 0 hours is very sharp absorptions, but we can see it's redshifted. So what does that mean? It means those ingredients, those components can give rise to wider band gap coming out of the materials. So it becomes redshifted. And this is an evidence actually to corroborate what we found in this XRD measurement. So when adding this kind of additive, we retard this kind of mechanism to occur. Also, on the other hand, we have identified delta phase FIPBI3 is very, very small, but it's rare. But before we talk about the further evidence regarding delta phase FAPBI3, it's not the perovskite phase anymore, it's actually a wide bandgap material. But one thing we observe is that we don't see the strong formation of lead iodide, because lead iodide is known to be believed the degradation product of perovskite. But if lead iodide is not the degradation product, what would that be? How comes we don't have lead iodide? Lead iodide is lead. So I'll come back to that point just in a minute. But we're going to first look at this kind of delta phase FIPBI3. So we did a very simple but interesting experiment, actually using just optical microscope. So we have halogen lamp. This is perovskite film, the schematics, and this is a real film under the optical microscope. We have some interesting setup. We have the UV light. So basically, the optical microscope equipped it with two different type of light source. One is a halogen lamp, the other one is UV light. So this is fresh control sample. So we see no difference. This is an age control sample, exactly the same conditions under the same microscope, but it's darker. Why? Because when the film is aged, it becomes rougher, and so the light will scatter, so it's darker. But of course, there are many, many more features that we can see here, like collider. But when we turn on the UV light, we see the blue emitting material. But the material we are making is around 750 nanometer. How this material gonna emit blue light? So essentially, we survey the entire the scan degrees with scan spectrums. So only this kind of delta phase FAPBI3 matching the feature of this kind of a blue light emitting materials. So we believe this is the delta phase FAPBI3. Okay, this is a modified film, the fresh one with UV light, without UV light. And this is the age one. You can see they are slightly different, but still they maintain the perovskite phase to the most part of the films. And okay, so this is fresh, this is age, and I put it side by side with both light arm. So with halogen light arm, with the UV light arm. So this is control. You can see the fresh one and this one, and this is the age one, and this is the modified one, and the fresh one and age one. Okay. But something we also observe is that when we look at the film, there's some bright spot. So it's just a simple slab because it's a upright microscope. So light coming out is the halogen lamp. So basically, they are holes. So identified by ICM, you can see it's very pinhole for our films. So when we have a hole, we probably will think about the scenario. Actually, we lost some material. We did lose some material, but what is left? So we did a very simple experiment. So we took some fresh and the iodide and we aged in nitrogen at 85 degrees using actually a LED lamp. So it's only 0.3 cent, but just under 6 hours, you can see totally discolor. So we did a little bit of study on that. We did some SRD measurement. So we actually see the iodide actually coming out of the iodide film. So basically, it becomes lead. We observe metallic lead in the film and lots of iodide ions. Then we went try to double check if this is something happening. So we prepare a perovskite and put it in thorium. We seal the vial. We put it in a sand aging machine, just like these two. So the one is modified, the one is controlled. This is after a while, but you can see the color is different in thorium. So exactly what happens. So we did some UV measurement, and you can see a peak coming out of 500 nanometer. Actually, it fixed the feature of iodide holes. So the iodide is not likely to be the agent product in this scenario. Why this is the case? Actually, when we buy the iodide, we can see, oh, we have to avoid light, it's a sensitive material. So when we combine light and heat, even there will be a tendency to form the iodide, but under that kind of circumstance, it's difficult to maintain the iodide. So the iodide will continuously to break down in this kind of harsh aging condition, combine light and heat, especially above 60 degrees Celsius. So this is the main findings. These are the main findings led from this work. Then, okay, so next things I gonna talk to about is regarding the perovskite is interface. And as we can see, when we change the perovskite compositions, what we have is it's a different bandgap material. And especially we focus on this kind of bandgap between 1.6 to 1.8. But we see a lot of photovoltaic penalty a couple of years back. Of course, in these 2 years, perhaps from last year or the year before, we see a massive improvement in terms of improve this kind of photovoltaic penalties. This kind of photovoltaic penalty is actually happens in many mechanisms, especially these two. So if today we take a perovskite as an absorber, we shine a light on, we generate electron and hole pairs, right? Then we have quasi-Fermi level splitting like this. Then we have electron transporting layer and also hole transporting layer. Try to take the electron and holes out of perovskite. But here, these charge carrier experience trapezoidal recombinations, also interfacial recombinations. So the voltage is not as high as intrinsically the quasi-Fermi level stability within the light absorber material. This kind of things even more severe when we increase the bandgap, because when we mix different materials, basically they don't like each other. We know about halide segregation. We talked about just in the previous work, and certainly we introduce more defect into the perovskite material. So this is why it reach certain level and it become plateau. So what we actually want, the perovskite could be just as good as the best semiconductor material, which is gallium arsenide. Gallium arsenide is so close to the theoretical limit, so the photovoltaic penalty is only 50 millivolt. So these kind of things, we have done some special treatment to the perovskite field. So it's basically a top surface treatment. Sorry, because the word is still under review, so I'm not able to disclose the molecule. But just like you have perhaps you have read some paper regarding perovskite, how to improve this kind of photovoltaic loss. We also achieve some very impressive values, especially for 1.6 electron volt, this kind of band gap, which will be the middle cells for triple junction perovskite cell. This kind of 1.6 electron volt will be the perovskite for perovskite silicon tandem. And for this kind of 1.77 electron volt will be the perovskite for lectin perovskite and perovskite, this kind of tandem solar cell. And something a little bit different here is we didn't make small pixels. We make a pixel at least the size 0.25 square centimeter or 1 square centimeter. For 1 square centimeter, we achieve similar level in enhancement. So put this into perspective, especially this kind of detailed balanced theoretical limits, we are only 100 millivolt below the theoretical limit. So essentially, we are extending what can be achieved in using gallium arsenide in perovskite solar cell, but just under exactly the same molecular treatment, especially a lot of preservation molecules, and they won't be able to apply to different composition. But here, this kind of treatment, we are able to do so. So this is just a benchmark against nearly over 1,000 data points, where we stand when we have this kind of treatment to enhance the VOC above what is available in literature, and also this is the PCE. But one thing to know about this is we use different shape to mark different pixel size, because when we increase the pixel size, normally we see a drop in terms of performance, PC, and VOC as well. All right. So this kind of treatment is actually non-solution process, is by vapor, and also we in my previous workplace they implement this kind of sextant, try to design for a causal tool that will be integrated into a fully evaporated sextants. Okay, so there is a says about perovskite, about solar cells. If we have a good solar cell, we're supposed to have a good line-emitting diode. So we actually took a very mediocre cell. You can see here it's only 16.6%, but it's a 1.8 EV cell. It's actually not too bad. So the highest one will be below 0.1 square centimeter and around 20% nowadays. So this one is the 1 square centimeter is a large cell. And you can see that JV curve is not so perfect. But if we use this solar cell, it's not optimized for line-emitting diode structures. So why I am emphasizing this point, because when we make a solar cell, we want to absorb as thick as possible, just not to over the limit that we won't be able to extract charge carrier. But for line-emitting diode, we want the emitting material try to be thin enough, so we'll have the electron and hole recombine. Like basically, this is the case. But we take a solar cell, which is quite thick. We inject charge carrier. As you can see, we sweep voltage from 0 volt to 4 volt. You can see it's uniformly emitting, and that line is around 700 nanometer. But something more impressive is that when we apply current injections, that is around 0.9 sound as is JSC. So you can see this is the emission photo. But over a time period of 600 seconds, it remains very good EQE. But the most important thing, the spectrum is right at the 700 nanometer during these 600 seconds. Why this is important? Because in order to get 600 nanometer, we are having 40% of bromide in its NL composition at least. So what will happen when we have this kind of mixed cation, mixed anion things? Normally, we will see phase segregations and also halide segregation, especially halide segregation. So this is kind of a state-of-the-art perovskite limiting diode using quantum dot. If it doesn't have any treatment, it just have this kind of segregation right away. So this is a work published by my colleague 3 years back. So the state-of-the-art preservation using quantum dot, small material, quantum size material, and well preserved to last for 10 minutes and 20 minutes. But something surprising us is that we have a thick film that is beyond 500 nanometer. We only preserve the surface. The halide segregation doesn't exist in this kind of circumstance. Of course, this is encouraging when we see this kind of result, but it might hint us, it might indicate the halide segregations actually it all come from the surface. So the surface is important. We touch up a little bit about when we talk about additive, we talk about the additive being pushed to boundary from the optoelectronic characterization, and I talk about maybe the from our analysis, the charge carrier of the opposite polarity. They have different concentrations. So one thing important is try to basically to remedy the interface and try to see if we will be able to reduce the amount of minority carrier at the interface. For example, if we want to extract electrons, so the important thing is try to reduce the minority carrier, which is a hole. Otherwise, the recombination will be severe. So this is most of the preservation functionality. Okay, so another thing I'm gonna just slightly talk about a little bit of our further work on different interface. The things I talk about are top surface preservation, because when perovskite forms, it gonna stop. So the top surface is always disrupted. So it's trivial. Of course, the community has been doing these kind of things for years. But of course, the bottom interface is also something people start working on, especially from last year or even the year before. So we took some inspiration from Thomas's organic field effect transistor. Try to use organic blends. Let organic blends will have this kind of separations between polymer. So it's an organic blend of polymer and small molecule. So when we blend it together, we'll have the small molecule and polymer to separate during the deposition process. So we have to implement this kind of approach, try to make our transporting layer at the bottom interface for a perovskite solar cell. And we use different kind of approach to form this kind of organic blends. So different conditions have different distributions of small molecule and polymer. But something interesting we found is that when we tried this kind of approach, well, basically we can align molecule in a way that is either face on or edge on, and depending on these kind of conditions, it further further affects the formation of perovskite. So we did a little bit of study using this kind of TRPL study. Actually, I labeled things wrong here. I'm sorry about this. I took the wrong figures. So the first one is actually illuminated from upper side. The second one is illuminated from the glass side. So basically, we have a glass, we have the transporting material, then we have the perovskite material. So when we illuminate it with actually 4 or 5 lasers from the films, and they seems to be the same. But when we illuminate it from the glass size, and the effective the target the TRPL, it seems to be better. So why this is the case? So essentially, when we have shorter wavelength excitation to apply to the materials, so basically some carrier will diffuse away. But when we illuminate at the surface, let we have our molecule to sit down to passivate, then we see the effect of the of this kind of molecule. So it does change the property of perovskite, because this kind of pure intensity is coming out from the perovskite, and at the bottom interface, then we will be able to modify that part. So this is actually still a former student. Now she studied at Oxford. Okay, so by using this kind of interface modification, we achieve even better performance. So our device can survive at 85 degrees in air encapsulated, and especially for our champion cell, it's 1500 hours to reach T95. All right, so we are approaching the last part, just a couple of minutes more. So we also look into the different way to characterize perovskite solar cell. One thing actually is quite common used in silicon industry is to use either electroluminescence or photoluminescence. Of course, photoluminescence, we don't need to operate the cell directly, that we can observe the cells using a photoluminescence camera. So we had this kind of setup actually to examine those age cells. So basically, we have a strong light emitting diode. Then we have a camera with a filter. Then we'll be able to measure the photoluminescence its intensity. So this is the we did a little bit of calculations. So when we talk about photoluminescence, we talk about its content yield, like photoluminescence content yield. Now you can see the massive difference between the molecules, passivation molecule, also the reference cells. This is the fresh sample. This is fresh sample. This is after 600 hours agents. So massive difference, because you can see a lot of area it seems to decay. But something important is that when we look at the photoluminescence content yield, we actually we are only looking at the certain part of the material, because most of the time we are looking at its open circuit conditions. But for solar cell to operate, we extract charge carrier out of the solar cell, out of the perovskite films. So we did a little bit of modification to this method. So essentially, we look into quarter-Fermi level splitting, and so we can easily get this kind of quarter-Fermi level splitting map from POQY. We identify also another physical property we call is collection quality. So essentially, it's when we measure photoluminescence, we measure it under open circuit, which is the most straightforward way. But also we measure photoluminescence under short circuits. So we define how many charge carrier can be extracted because for open circuits, we expect the film to be very luminescent because the charge carrier, they are accumulated within the film. And open circuit, we don't collect any charge carrier. But for short circuit, the film is supposed to be very dark. Then we did this kind of calculation. So basically to examine how many charge carrier to be extracted out of the film. So it might not be too straightforward to look into just these math because when we do the comparisons, actually, when we have the quasi-Fermi level split, and we don't have massive differences, and when we look at the quasi-Fermi level split, but when we look at the collection qualities, they are very different. So we are trying to identify what kind of physical property that we can use to further quantify and better to predict this kind of degradation process, especially for early diagnostics. All right, so this is my talk. It's a bit here and there. I hope I still have you here and focus the very last bit. Of course, I'm happy to take all the questions. Thank you.
Thank you very much, Yen. It's a very nice picture, this one, no? Because we can see a lot of people that they have participated in our summer schools, back there. So I would like to ask the people if you have any questions. George Kakavelakis, the floor is yours. Thank you.
Thanks, Lynn. Excellent presentation. I mean, especially the first part that, I have seen your paper in Science, but I'm really surprised with your work on the lead iodide, especially. Congratulations on this. And I'm wondering, first of all, my first question is related to the composition. So you mentioned this perovskite was mixed a cation, mixed halide, right? So have you,
Yeah.
and my question is like, I mean, we have seen recently the high records, 25, 26% based on formamidinum lead iodide perovskites. So have you tested this hyperidinium passivation strategy with the high efficiency devices? And the second part of my question is, I understand this is like a bulk passivation strategy. So you incorporated your passivator inside the bulk of in the precursor solution. Have you also tried to incorporate on the top surface of your perovskite?
You mean this one or the next one? The
No,
second question.
The second question is related to this part as well.
I see. So basically, we did try to incorporate this kind of an additive and also some similar one to different compositions. So it goes as low as 10% or 5% bromide. Regarding if we have more success in pure or maybe pseudo FAPDI3 pseudo FAP. In terms of performance, maybe not. Even back then, we see the performance enhancement is not so dramatic. It's like relatively maybe 3 to 5%. So this is the case. But of course, we still continuously using this kind of additive in some of the work because it does enhance stability. But as for performance, after these years, the improvement we can consider is maybe minimum. So I don't know if I cover everything here. And George, also, I would like to mention mention one thing. For this kind of FAPPI3 work, especially published last year, like so many impressive work, 25 or 26%, especially for inverted cells. But one thing I do notice is that when they do a stability test, a lot of times they switch to slightly different architectures, and we see a drop because we did a little bit of statistics. We see a drop in terms of the if they did report the performance for their cell for stability tests, it's like around 10% difference in terms of efficiency. This is something I'm more puzzled with. I don't know if you notice about that part.
Yes, indeed. I have seen many of these papers, like they're playing a bit with the composition in terms of the JV result and the stability result. So we have to be very cautious about it. But what about my second part? I mean, about the passivation strategy. You mentioned you incorporated in the bulk, but what about the surface? In this case, there was no surface passivation, or it was also passivated with this piperidinium molecule?
So, okay, this is the second question. We basically would blend it with perovskite precursor, and for the device here, we don't passivate bottom, we didn't passivate any part. We just add additive at a time into perovskite material itself. So this is the case. Do we have a new knowledge about this kind of passivation? Can we do it at the interface? And we did try, like, because before this word, there is also another word, BNI and BFO. So we did try different approach to see if we work at the interface, but the interface is relatively difficult to control its amount. So because it can be blended into perovskite precursor, so if we put it at the bottom, it will partially dissolve into perovskite material, but it also remain a little bit like particle alike at the interface. Can we put it on top? It will be a little bit difficult because you can partially dissolve perovskite itself because it's only liquid. If we use different kind of additive, so but new knowledge, we did have a further test about its whereabouts because it might have further interactions with different type of, for example, HTM, and it also influences its distribution a little bit because at the time we only study still like a polymer stage, like PTA before the era of the famous Me4 pack or 2-pack or Mio 2-pack, the SAM HTM age. So this is the case. It does have certain influence or interactions with the molecule underneath. So this is the case. Then I suspect it affects its distribution across the bulk as well.
Thank you very much. And just a final, just out of curiosity, these TOF SIMS measurements are done in a device or in film level?
So it's half stack. So basically, not device level. So if we say, yeah, it's film.
Okay, thank you very much.
Thank you, George.
Thank you very much, George, for the question, and Ian for the responses. I would like to ask you something, Ian. You mentioned that a good solar cell is a good LED. Am I right?
Yes.
And you explain why, and I totally agree. But I would like to ask you, in one of our papers, we have made the following statement. A bad solar cell is a good perovskite sensor. What is your opinion about this?
What a big solar cell is a good perovskite sensor.
I mean, gas sensor.
Gas sensor. Well, if you talk about back perovskite. I don't know if it's exam, so I'm interview. So the perovskite back solar cells we can think about maybe contains more defect.
Exactly.
And you have more defect, you have more trap state. And do you have more trap when you have more trap state? Can you capture more different type of analyte, no matter in what form, gas sensor, maybe gas analyte, so you will be able to fill the trap. So essentially, we change the current voltage behavior. So this is the scenario. So maybe some perovskite resistor is also like this.
And I would like to ask you something else. How does the
And
energy band gap affects the stability of the perovskite?
sorry, I didn't catch the first part.
How much the energy band gap, if this is the case, affects the stability of the perovskite?
Oh, so essentially, when we have a different band gap, we need to mix, like for example here, we need to mix a lot of bromide here. But not just change the bromide, because we also need to think about if the A side is working. So when we add more, and they have different solubility, if we have using solution process this kind of route, so you just make everything difficult from the beginning. Then its crystallization is just very different. I know I'm talking about processing, but when its crystallization become difficult, the film become rough, and we are expecting we don't form very good crystal. And we essentially from processing we already created defect because we don't know how to process it in a very good way. So even we have so many different kind of atoms and different molecules. And from energy point of view, entropy, they just want to stay together. So we have phase segregations, we have halide segregations, then we have defect. So then we have so many different things just like competing to destroy the perovskite. So itself is not so stable. Just like what George mentioned about FAPBI3, it doesn't have the issue with halide segregation because it doesn't use bromide. So what it has is a phase issue, but for mixed cation, mixed anion, when we need to deal with it, we just facing many more difficulties that due to different kind of atoms, elements that we use in order to get wide band gap. So this is the case.
And my final question is the following. I mean, when you said about the photovoltaic penalty, what is the physical meaning of the photovoltaic penalty?
Oh, just because we are hoping we are incorporating this kind of different elements in, for example, more bromide, not just iodide. We have more bromide. Then we are expecting it has a wider band gap, so bigger output voltage, which is VOC, but we don't reach that. We just make a beautiful 10. So this is the penalty we are getting because we put in our effort, we pay the price, but we didn't get the things we want. But what we get is a penalty in our photo voltage. This was the case like maybe a year ago. Last year, I think a lot of work they are doing very good and also try to preserve the defect. So basically they reach the same level as the photo voltage I just showed. So this is the case.
But there is no physical meaning behind this.
But Costa, sorry to interrupt. Lynn didn't mention photovoltaic penalty. He mentioned photovoltaic penalty.
Yeah.
I got it, photovoltaic penalty, but even photovoltaic penalty, what is the physical meaning? What is the physical parameter behind this? How can you solve it?
Can I reply?
Yeah.
Yeah, it means when you have higher band gap, but the VOC doesn't increase. This is the photovoltaic penalty.
But the VOC is not linked with the energy band gap?
It is linked, but when you don't have good crystals or good interfaces, even though you have a higher band gap, the VOC you get is smaller, so you have a penalty.
So it's not a, it's like fabrication deficiency then?
Yes, exactly.
Okay. Because in the, yes, okay, I got it now. But this should have a reflection also to the short circuit current in this case, no? Because if you don't have good interfaces, this means that you create problems to the transportation of the photo-generated carriers.
No, but these defects are mainly in the bulk.
So it's not in the interfaces then.
Sorry?
So it's not in the interfaces because
it can be in the interface, but the bulk plays an important role.
So, but in case that is in the interfaces, you should see an impact.
Yeah, you should see a drop in the current also.
Yeah. All right. Thank you. My dear friend Lynn, I have discovered that I have messed my emails. You know, a lot of people, I thought that I have sent the email, but you know, a lot of people, I don't know where my emails have gone. So because I receive messages like, where is the link? So I'm sorry about this. You know, I will upload the video recording, you know, in the YouTube when you will provide me the green light. It was
okay. Thank you.
It was a very nice talk, very nice organized. I have to say I was very much impressed by the technology and you know how you map and visualize your results. This was like impressive.
All right. Thank you.
Congratulations, Lynn. Very nice work.
Thank you, George. You have very nice. Thank you. All right. Thanks, everyone.
Thank you.
Bye.
Thank you. Bye. Have a good day. Bye. Bye now.